Welcome to Math A to Z. Our topic of today's lecture is convergence of series of alternating term and series of arbitrary term. Now, what is alternating term? Alternating term series. The definition of alternating term series. If un greater than 0 for all n belongs to capital N, then the series -1 whole to the power n minus 1 into un, that is u1 minus u2 plus u3 minus u4 to infinity. That is alternately positive and negative, positive and negative. This type of series is called alternating term series. That is alternately positive and negative. Now we discuss the test of convergence of alternating term series. Here, an important test of convergence of alternating term series named LIBNITZ test. LIBNITZ test of convergence of alternating term series. And the statement of this test is: if sequence un is monotonic decreasing and of a sequence of positive term, and limit n tends to infinity un equal to 0, that is the general term tends to 0 as n tends to infinity, then the alternating term series must be convergent. Okay, so the statement of LIBNITZ test is: if un be a positive term monotonic decreasing sequence and the general term of this sequence is tending to 0 as n tends to infinity, then LIBNITZ test state that alternating term series -1 to the power n minus 1 into un must be convergent. Now we go to the proof of this state, that is LIBNITZ test. Here we consider sequence of nth partial sum, that is nth partial sum Sn equal to u1 minus u2 plus u3 to plus -1 to the power n minus 1 into un. Now if we take S2n, that is 2n partial sum, then obviously u1 minus u2 plus u3 to, obviously this term is -1 to the power 2n minus 1 into u2n. Okay, so -1 to the power 2n minus 1, since this is odd, so this must be negative, that is negative, so the previous term must be positive. Okay, Now S2n plus 2 equal to, here all the term as usual, and then after u2n plus 1 minus u2n plus 2. Here S2n plus 2 minus S2n equal to, here remains this two term and all the term of this sequence, this term and this term must be cancelled. So here we get u2n plus 1 minus u2n plus 2. Here in statement we say that un is monotonic decreasing. So this must be less than this. That is, this is greater or equal to 0. Imply S2n plus 2 greater or equal to S2n. So we say that S2n, this sequence must be monotonic increasing. Monotonic increasing sequence. Also, from this, if we arrange the term as u1 minus u2 minus u3 minus u4 minus u5 and similarly minus u2n minus 2 minus u2n minus 1 and last term is minus u2n. All the term u2 minus u3 greater than 0 or greater equal to 0 because this term is less than u2 and this is greater equal to 0 because u5 greater than, u5 less than u4 and so on. So we can say that S2n greater equal to u1. Okay, sorry, S2n less equal to u1. And from this condition we say that since this is fixed, so this condition we say that sequence S2n is bounded above. So this is monotonic increasing and bounded above. So it must be convergent. Okay. Now we consider S2n plus 1. Then similarly we get this is u1 plus u1 minus u2 to minus u2n plus u2n plus 1 and S2n minus 1. This is u1 minus u2 to u2n minus 1. Now subtracting this from this we get S2n plus 1 minus S2n minus 1. This is equal to minus u2n plus u2n plus 1 and this term is less than this term. So this result is negative, that is less equal to 0 for all time. Imply S2n plus 1 less equal to S2n minus 1. So the sequence S2n plus 1 is monotonic decreasing. Also, from this relation, we can write this as u1 minus u2 plus u2 minus u3 to u2n plus 1. That is greater than u1 minus u2, because all the term are positive. So we delete all the positive term, that is right side is less than the left side. So we say that this sequence is bounded below, that is bounded, right? So this sequence is monotonic decreasing and bounded below, so must be convergent. That is, we say that the sequence S2n is monotonic increasing bounded above, and sequence S2n plus 1 is monotonic decreasing bounded below. That is, sequence Sn is convergent for all n belongs to capital N. Right? Now we can write S2n plus 1 minus S2n equal to U2n plus 1. Here is only one term left and all the other term be cancelled. And taking limit on both sides, we get limit n tends to infinity S2n plus 1 minus S2n equal to limit n tends to infinity u2n plus 1, and this is given equal to 0, because from the given statement we have limit n tends to infinity un equal to 0, that is limit n tends to infinity u2n plus 1 equal to 0. Hence limit n tends to infinity S2n plus 1 equal to limit n tends to infinity S2n. Okay, that is both the sequences convergent and converge to the same limit. So we can conclude that the sequence Sn is converged for all n belongs to capital. And since the sequence of nth partial sum is convergent, so we say that the series, that is minus 1 to the power n minus 1 into 3, this must be convergent. Okay, this is the proof of LIBNITZ test of convergence of alternative series. Now we apply this test in an example. Consider the series 1 minus half plus 1/3 minus 1/3 through infinity, and this is minus 1 to the power n minus 1 into 1 by n, right? Here is a summation n equal to 1 to 3. Here un equal to 1 by n tends to 0 as n tends to infinity, and sequence un is obviously monotonic decreasing. Okay, so by LIBNITZ test we say that this series is convergent. This series is convergent. Now we another series which is called arbitrary term series. Arbitrary term series. In an infinite series, if there are in an infinite series, summation even, if there are infinite number of positive terms and infinite number of negative terms, then this series is called arbitrary term series. Okay, there is no rule for negative and positive. So in this series, there are 2 term positive and 5 term negative. Then after also 3 term positive and 9 term negative. Arbitrarily positive and negative term are there. So this type of series is called arbitrary term series. Okay. Here we give an important definition of convergence of absolutely convergent series or absolute convergence of series. Okay. An infinite series summation event is called absolute convergence. If the series summation mod event is convergent. Okay. Summation event is called absolutely convergent if summation mod event is convergent. So it is clear from the definition that if the series event is a positive term series, there is no difference between convergence and absolutely convergence. Okay. If in a series if for a series summation mod event is not convergent, but that is not absolutely convergent, but if summation event is convergent. Okay. If for a series summation event, infinite series, summation mod event is convergent, that is absolutely convergent, but summation event is not convergent, then this is called conditionally convergent series. Conditionally convergent series. Or another name of conditionally convergent series is semi-convergent series. Okay. So here summation event is not convergent, that is not absolutely convergent, but summation event is convergent. This is conditionally convergent series. Now we state a important theorem about absolutely convergent series. We say that an absolutely convergent series must be convergent. Okay, this is the important theorem about absolute convergent series. If a series is absolutely convergent, but then the series must be convergent. Now we prove of this theorem. Let summation event be an infinite series containing positive and negative term. Okay. Here summation mod even is convergent. It is given. So it is a convergent series of positive term, obviously, because all mod even is positive. Now we know that un plus mod even, okay, un plus mod even equal to either 2 into un or 0. If un greater than 0 and if un less than 0, right? So we say that in the series summation un plus mod even, every term are greater or equal to 0. Either 2 into un if greater than and or either 0. That is, every term of this series is non-negative. And we always know that un less equal to mod un for all n belongs to capital N, right? So we can write un plus mod un less equal to 2 into mod un plus mod un using this result, that is un plus mod un less equal to 2 into mod un. Now if we compare this series and this series, the general term of this series is un plus mod un and the general term of this series is mod un, and we have this less equal to 2 into this, right? So by comparison test we say that if this series is convergent, then this series must be convergent. This is the comparison test in general form, and it is given that this series is convergent because this is convergent series of positive term. So we must have this series is also convergent. Okay, so we get that this series is convergent. Summation un plus mod un is written as summation un plus summation mod un. Here this series is convergent, it is given. Also this series, that is the sum of these two series, is convergent. So we must have this series also convergent. Summation un is convergent. Okay, so this is the proof of this theorem, that is an absolutely convergent series must be convergent. But the converse of this theorem may not be true, because the definition of conditionally convergent series here not absolutely convergent but this convergent. But if this series is absolutely convergent, then the series is obviously convergent. Okay, now we go to 2 or 3 most important examples. If we consider summation minus 1 to the power n1 by n square, here un equal to minus 1 to the power n to n square, if this and this. Okay, now mod un equal to 1 by n square, then summation mod un equal to summation 1 by n square, and this is convergent because this is P series with P equal to 2 greater than 1. So this is convergent series. That is, we say that by applying the above theorem, this series must be convergent because the series is absolutely convergent, so the given series is convergent. Also, summation sin nx by n square. Here mod un equal to sin nx by n square, and this is n square, and by using comparison test we say that summation mod un is convergent. So this series must be convergent. Okay, these two important example of the absolutely convergent series. Now we go to the important example of conditionally convergent series. Okay, if we consider summation minus 1 to the power n into 1 by 2n minus 1. Okay, and if we take absolutely convergence of this series, then we get mod un equal to 1 by 2n minus 1, and summation mod un is equal to this, and this is obviously divergent series. We get this by Cauchy's general principle of convergence. So this is not absolutely convergence. But if we test this series of alternative terms by applying LIBNITZ test, it is clear that 1 by 2n minus 1 is monotonic decreasing and tends to 0 as n tends to infinity. So it must be convergent. So this alternating series is convergent. That is, the original series is convergent, but the absolute series is not convergent. That is not absolutely convergent. So this is the conditionally convergent series, and we say that this series is semi-convergent. And another important example we take here: summation minus 1 to the power n minus 1 by n to the power p. Okay, if we take p greater than 0, then here this series is taken as alternating series, and this is un, then un equal to 1 by n to the power p. So this is monotonic decreasing and tends to 0 because n greater than 0. So by LIBNITZ test, this is convergent. But if we consider the absolute series, that is mod un equal to mod minus 1 to the power n minus 1 into un, that is 1 by n to the power p. And summation mod un, that is summation 1 by n to the power p, is p series, and we know about this series: if p greater than 1, then it is convergent, and if p less equal to 1, then it is divergent. So if p greater than 0, then 0 less than p less equal to 1, it is divergent, and when p greater than 1, it is convergent. So this is not true for this case. So it is not absolutely convergent for p greater than 0, but it is convergent for p greater than 0. So this is also a conditionally convergent series. Okay, thank you very much. Thank you for